Back after the coffee break, and I am pleased to welcome on stage Mr. Antonio Abad, Chief Technical and Operation Officer at Hispasat. You can give him a warm round of applause.
Thank you. So, good morning. First of all, thank you for your kind invitation to this event. It is the first time I'm in this meeting, which appeared to me as an interesting opportunity to share some of the things that we are doing. Because it is the first time I am in this forum, I wasn't really sure on what is the scope, and I realized with the initial speakers that there are like two angles for this story. They've been talking, most of them, they've been talking about the way to secure space, and I'm gonna change that angle because today I would like to talk to you about space for security. Not secure space, but space for security. What can space bring to us in the security world? So, because I think this is a well-educated forum, I'm not gonna get a lot in the discussion on why do we need to rebuild all the classical cryptography that we had. We know that the evolution of quantum computers is gonna make us rebuild this cryptography in the next years. There are clearly two trends, and I've seen that there are people talking about PQC in the event. And I'll be talking about QKD, sorry. I just wanted to make a statement clear to say that PQC, QKD, they are not antagonist solutions. They are solutions that complement each other. I'm gonna talk today about QKD because this is what we are putting our main focus today. But we are also discussing with other people about some potential evolution of some PQC systems. So you will hear us also about PQC in the next month, probably. But again, we're going to focus on QKD. At the end of the day, what we are doing is we are using QKD because we know that we can code a message into quantum properties of the matter. In our particular case, we are using the polarity of the photon. But we know that we can code this information in quantum properties, and when we are transmitting them, the receiver can make sure by 100% that the message has not been read before. So this is the main advantage and the real essence of the QKD systems. And these QKD systems are being deployed in QKD networks nowadays, and there are people in Barcelona, Lux Quanta, they are building QKD modems already, where you can create and connect to QKD networks. And Telefonica has deployed a local QKD network in Madrid that is operating with real traffic. So they are using a commercial fiber network with real traffic, and they are putting on top of that QKD messages, and this is working well. So there is an interesting future for this system. But there is a limitation in ground QKD networks. And that limitation is bringing an opportunity to the space systems because you can see in the chart. Can I point somewhere? I don't know. Well, you can see in the chart in the upper left that the losses in red are the losses in a telecommunication fiber that are dropping with the distance, while the losses in the space, in the free space, they remain quite stable. This is why when we exceed distances beyond 100 kilometers, it is impossible with the current technology to connect and to transmit photons and make QKD beyond that distance. Because of that, we have this chart, this drawing, where we're showing that the satellites are feeding some local nodes that will relay the messages in the urban areas, while for interurban areas, the satellites will become the tool for transmit these QKD messages. I have included a classical prepare and measure sequence in the chart on the right. Essentially, what you have is that first we are transmitting the key to one of the stations, and second we are transmitting a second key to the second station, and we use that second key in order to convolute the first key that is then transmitted to the second station. So once you get the two keys in the two places, you can exchange securely the information you want. This is what we call prepare and measure, or BB84 as the protocol. And clearly, and this is the main message, the satellites will configure in the next years as a perfect complement to the terrestrial infrastructure. In particular, in Hispasat, we are focusing in geostationary satellites for QKD. Since 2016, that the Chinese flew the Misius mission, and I will come back to the Misius and the last news about Misius in the last days. But since Misius in 2016, there have been several countries, including the US, including Canada, including some German initiative, and some future initiative from Singapore, and even there is the European initiative, Eagle One, from our friends of SES that is expected to fly next year. So there have been several initiatives in LEO. In Hispasat, when we started to work on QKD, we decided to start directly in GEO. And we did it because there were many initiatives that were already running on LEO, the first one with Misius. And what I wanted just to claim, you probably I'm not a security or a cryptography guy, but I think that most of you have probably read the news that now people are questioning the security of Misius initiative. There was a paper published some days ago. I've been checking with our experts just to share with you that we understand that this is something that is true, that it has some vulnerabilities, the Misius initiative, due to the use of several lasers. Since the initiative on 2016 from missions with several lasers, I think there is another mission from China that is already using a single laser and is covering that vulnerability. And I think nowadays everybody is focusing on a single laser. So I think the headline is very exciting, but there is really nothing to worry about that, because it is something coming from the early days of the Misius initiative. But I was trying to explain you why we decided to went to GEO. Essentially, you have in the chart, and you can see there, that the coverage of a GEO satellite is approximately 1/3 of the global Earth. So while the coverage of a low Earth orbit satellite is like a radius of 1,000 kilometers or something like this, in a GEO satellite you can see 1/3 of the Earth at the same time. And that is giving you the possibility to connect to several locations in a short period of time without waiting for the pass to occur in the location. You know that because LEO satellites are not seen from the ground as a fixed element in the sky, they are passing, and the pass is like 5 to 7 minutes. So you have 5 to 7 minutes to acquire the satellite, to lock onto the satellite, to make the key, and then to handle to the next satellite that will pass with another 5 to 7 minutes. is a bit more complicated. It's way more complicated, the management of the key distribution with LEO satellites that you can make with GEO, that are satellites that are fixed in the sky, and you're pointing to a point in the skies, and you have 24/7, the satellite is there, and the satellite will be doing the transmission of the keys for the time that's needed for that. So this is at the end, because of this easier management, is a great advantage of the GEO satellite. The other thing, as we are showing in this chart, we are showing two drawings, one on the left with the classical prepare and measure protocol, and the one on the right is showing that from GEO orbit, we can make entanglement protocols that essentially consist in that we are not sending one photon at a time to one of the locations, but we are sending two entangled photons at the same time to the two locations. That makes that you don't need to store the key in the satellite. And that is making that the satellite will not need to be a trustable node, which is a very relevant advantage for the future evolution of the QKD, to have satellites as non-trusted nodes. So this is why we've been working in GEO satellites, and we defined our program that is called Caramuel. It's a GEO QKD program. It's Caramuel. Caramuel was a Spanish bishop in the 17th century, and he was writing the first cryptography treaty in Spain. And this is the name of our mission. The key of this mission is that it is the first geostationary QKD mission from space. We are expecting to integrate that and become part of the EuroQCI of the European initiative. And I think that the most relevant elements of these programs is that we have taken into account since the very beginning the role of the ground networks, and we are working with Telefónica and Cellnex. Cellnex is a Spanish towering company that is also working on the development of ground QKD networks. And we're also working with potential customers. Initially, we started working with the banking industry, with Santander and BBVA. And now we are working also with critical infrastructure operators. We are working with Red Eléctrica, and we are working also with Elia, the Belgium operator. And we are discussing also with the Nuclear Security Center in Spain. So there are certain operators of critical infrastructure that are helping us developing the use cases and designing the system. And of course, we are working with the National Cryptographical Center in Spain that is helping us supporting the future certification of the system. We are expecting to launch this system by late 2028. And essentially, we are considering two scenarios that we are showing in this chart. One scenario is that, we have seen before, we can deliver two keys to two different locations, and those locations will require to use ground telescopes. Because we are in GEO, you can imagine the link budget is not simple. Some people, 2-3 years ago, were saying it's not going to work. We have demonstrated that it's going to work, the link budget, but we still need relatively large telescopes, like 1.5 meters. So 1.5 meter telescopes on ground. So it's not something to be used for everybody. So this is for high security applications. We'll use those telescopes directly. And the second scenario, which is a more commercial scenario, is we'll have nodes as we have shown before. And we have put here a typical case that is a connection between Madrid and Barcelona. In Madrid, we have the QKD network from Telefónica. In Barcelona, Cellnex is trying to deploy a QKD network. So they will have nodes that will receive the QKD keys in their nodes, and they will relay those keys in their ground QKD networks, so that then the user at the end will only require to have a QKD modem to receive the keys. And then the customers in Madrid and Barcelona, they will exchange secure information with the keys that has been delivered with the modems, with the local modems. What is the current situation of the program. So we have created a consortium at this time of Spanish companies, because this is mostly done with the Spanish funding, and as I will explain. And we are combining three main elements in this consortium. On the right, we are combining the academia. For the QKD, the knowledge is not yet in the industry. In the industry, people are working in QKD initiatives, but still the main knowledge and development is in the academia. This is why we are working with the Polytechnic of Madrid. We are working with the Astrophysics Institute of Canary and the Vigo University, where we have some of the internationally known experts in those universities. We have all the space and secure industry that you can see on the right side. And there on the bottom, you see Telefónica and Cellnex as ground network operators, and the banking industry with the National Cryptological Center. So some technical information about the system. We'll already mention that it's a prepare and measure. We are using discrete variable, like many of the, not all, but many of the systems are using already discrete variable because they have less low losses. Protocol BB84, wavelength 1550 nanometers, onboard telescope aperture onboard is 450 millimeters. We are using a bidirectional laser beacon, and we are using authenticated RF for the distillation channel. And you can see the block diagram. I'm not going to detail the block diagram. If somebody has some interest, I can explain and share with you later. So as I was saying, what is the status, the current status? There are different phases in the program. We have run phase 1 for the last year. We are currently in the flight segment PDR. We finished the flight segment PDR, and we are validating the breadboards currently. We're expecting also this month to cover the PDR for the ground, and we're expecting the ground CDR to happen after summer and flight segment CDR early next year. The idea is to finish the program with the delivery of engineering models plus for the payload part in June next year. From there are some future phases that still need to be funded. They are expected to be funded in the next ministerial, like the finalization of the flight models. The flight models are currently in development, but they won't be completed in the phase 2. They will be completed in phase 3 with the integration of this on the hosting satellite. And then they will make platform accommodation and launch in phase 4. The idea, and I haven't shown here, but the idea is to launch this, it's somewhere else, to launch this by late 2028, okay? Also worth to mention that we're gonna run on-field testings on ground early next year from La Palma to Tenerife, to the telescope in Tenerife. We'll install the payload in La Palma, and then we'll point to the telescope of Tenerife, and we'll make some link test from there. I have already some elements, some building model and mock-ups from the system. There is an initial one in plastic. We have in the middle, we have now, this is the current model that we have. It's a 1-to-2 model, and we presented this in the defense fair this week in Madrid. We are presenting it in this fair, and we have an artistic view on what is it going to look like integrated in the satellite. I mean, you can see that there is the telescope, that is the big cylinder, and you can see the different electronic boxes with the optical heading of the telescope, the processor, the interface unit with the platform, the source, the photon source. I mean, you have the different elements there. And yes, another program that this is about the GEO system. In parallel with this GEO system, we are just starting a new program in this case with the European Space Agency, where we're going to make the integration of GEO and LEO QKD systems. And for that program, we are cooperating again with the academia, with the ICFO, the Institute of Catalonia Photonic Optics, and the Polytechnic University of Madrid. In the industry, we're working with Thales, Indra, and GMV. And then we are working with Spectral, with the Singaporeans, with SCS for the Eagle One, and with S4, that is from the DLR. They have flown a CubeSat. It's not that CubeSat is not able to deliver QKD, but at least is helping us validating the optical link budgets. For the certification, we're working with the Cryptographical Center, the networks with Telefonica and Cellnex, and again with the users as we've done in the past. And let me finish showing you a block diagram of what we are building. Essentially, the basic idea is that we'll be creating a service center that will be in charge of receiving the orders from the customer. And in the back end of the system, there will be a sort of orchestrator that, depending on the requirements of the specific requirements of the customer, this orchestrator will decide to route the requirements, the service requirement, either to a GEO infrastructure or to a LEO one, and depending on which LEO one is available and more suitable for this specific service, it will route it to the specific service. And then this system will provide the keys to the ground QKD node that will relay the key via the QKD ground network finally to the two users so they can exchange secure information with that. This is the principle of what we want to do. And I want to finish my speech here saying, I mean, we are not technological development companies. We are a satellite operator. We are a service provider. What we want to do with all that is we want to use the technology, in this case, the quantum key distribution technology, for providing secure communications to our customers. And we'll do it with the LEO, we'll do it with GEO, and in the future, we'll do it with PQC, depending on the different requirements that our customers will have. And I will leave it there for the moment, and we'll give you the opportunity to make some questions. Thank you very much.
Thank you very much, Mr. Abad. You can come on the center of the stage. So, to be fair, I will also share your history. So you've built all your career at Hispasat, from a satellite engineer to a mission manager, and finally to the Chief Technical and Operations Officer you've been since 2012. I shall also mention that you're the Vice President of the Spanish Association for the Space Industry, ProEspacio. Thank you for sharing your views on developing wide...
And if I may, just two words. One, I am too old, as you have recognized, but I'm older than John saying, because I haven't spent my whole life. I started working, I want to recognize my old friends of Telefonica. Initially, I was 3 years in Telefonica before I went to Hispasat. It's true that I have spent most, but not all my...
Not all, yes. And since Telefonica is still part of your ongoing projects, it's important to mention. Thank you. Thank you for sharing with us the layout and having us the premiere of this Caramuel project. We have indeed questions from the room. And the first one is from Einar Andreas Overnus. He asks, is there a need for the GEO QKD transmitter to accurately point to the two simultaneous receivers, or can any two or more receivers pick their shared QKD keys at any time?
Wow, that's an interesting one. Let me see if I understand. I need to accurately point. Well, let me try to answer the question. The short answer is yes. The laser that is emitting the photons is a narrow beam laser that need to be pointed to the specific place receiving the photons. So you need to wait till the onboard telescope is pointing to the ground in order to receive the photon. So it's not something that you can choose when you want to receive them, because you need to coordinate with the satellite to make sure that the satellite is pointed to you and sending the photons.
Thank you.
So sorry, I think it's a bit detailed, but I'm glad to answer the detailed questions.
Yes, sure. Do not hesitate to raise any interrogations you might have. The other one is from Mike Dovey, and he asked, what are the challenges with QKD when it comes to satellite constraints such as swap, size, weight, and power?
Yes, in terms of the major challenges, for us, as you may imagine, I think that the technology is currently maturing reasonably well. The difficulty that we are having today is what we are calling, I'm not sure if the term is correct, but is what we are calling a spatialization of the electronics. So we have electronics on ground, we have sources, we have photon sources that are working unstable on ground, but we need to make sure that those photon sources are working well and behaving well when they are exposed to a radiation environment and when they are exposed to different temperatures in space. So definitely, for us, the current major challenge is related to adapting the current technology that I think is reasonably mature, adapting that technology to the space environment.
Thank you. We also have a question from Tom Stabary, who would like some more information, and for you to be specific, in which platform will you perform the entanglement you presented earlier? Is it on the satellite? And if so, wouldn't it make it a critical asset?
No, on the contrary. The question is, yes, we'll make the entanglement on board of the satellite. On the contrary, this will make the satellite not to be a critical asset. Let me explain this. When we are using the prepare and measure, and I explained that at the beginning of the presentation, we need to send a key to one of the users, and then we need to store the key on board. And with that key stored on board, we need to wait for the next pass on the second location. And when we are in the second location, then we release a new key and we convolute the second key with the first one that was stored, and then only at that time we can release the key from the satellite. So there is a period of time where the key needs to be stored in the satellite, and there is where the satellite becomes a critical asset. However, in the entangle protocol, we are creating the key with a QRNG, and we are transmitting with two entangled photons. We are transmitting the key simultaneously to Alice and Bob, if I may use the lingo, the cryptography lingo. You are sending simultaneously to Alice and Bob, and I don't need to store anything in the satellite. So if somebody tries to access the satellite, it will be impossible to get the key from them by accessing the satellite, because the key is never stored in the satellite. I hope it's understood.
We have 1 minute 30 left, and so I will project the question from Alexandre Mej, but I will also build on his question to ask one from Jordan Trom. So, question from Alexander Mej is, QKD protocols rely on authenticated links to exchange information. Those links require classical shared secure crypto keys between parties to work. And since those crypto keys are already there, why use QKD rather than classical crypto? Which leads us to the second question. What is the market size of the application you described? And what is the customer interest, commercial customer interest you see?
First, let me thank Alex for the question, because I wouldn't think I was in a cryptographical seminar if I don't get that question. Thank you for the question. That's an interesting one. You're fully right. Authentication is one of the elements where we need to be careful. It's not a major issue. What is our view about authentication? I'm not thinking we are going to rely on classical cryptography, sorry for that. I'm thinking we will rely on PQC for authentication. And you say, but then what the hell? Why don't you use PQC and you get rid of that bloody stupid QKD? The reason is the following. Because for the authentication, I need a very short period of time where the key needs to be secure. And there, I still believe that PQC can work well. With QKD, you will assure to 100% that nobody else knows the key, and it will be valid as long as you can keep it stored and secure from the rest of the world. I don't know if I explained myself. QKD, I said it at the beginning. We are not discussing about PQC versus QKD. We are discussing that they are complementary, and certainly we will use PQC for the initialization of QKD systems. Okay? And
the commercial interest?
And the market size, this is one of the things that we are working currently. What I would say is that we don't have a number, and between brackets and low voice, I won't tell you if I knew. But what it is clear is that if you want to have a certain level of security, you shall go to QKD. PQC, you will never be 100% sure that it is safe, because PQC is something that, if you give me 30 seconds, I will explain why. PQC is something that will last for a period of time. At the end of the day, what we are doing is we are building PQC because somebody broke classical cryptography. And it is almost sure that it is a question of time and a question of computer performance that in the future, people will be breaking PQC. So PQC is something that will need to be renewed from time to time. And you will never be sure when it is broken by somebody. If that somebody is not announcing that they've broken it, they can keep breaking your codes without letting you know, and that will be the most insecure situation.
And we want to know. Thank you very much, Mr.
Thank you.